Hello, this is the notes for section 3.3. And we'll talk about a few things, but the main thing is we are going to talk about the power rule. I think your book calls this techniques of differentiation, but this is the main one that we're going to talk about, and we'll do lots of examples and get a little bit of other notation stuff down. Okay, so first thing I want to consider is what's happening, or what do we have, what do we see in common, what kind of patterns do we notice when we take the derivative of a polynomial. And you remember what that means, what a polynomial is. A polynomial is a function that looks like this, where f of x is equal to some power of x plus a number times the next down power of x. And that could be 0, one of them could be missing, it could just be like x squared, whatever, but it's something anyway that in general looks like this until you get all the way down to finally, right, and these are just constants. That's not, of course, E, Euler's constant, 2.71828. It's just a constant, right? So it's something of this form. So you might have noticed a pattern when we took derivatives using the definition of the derivative. And we want to generalize that pattern and make a rule that we'll call the power rule for taking derivatives of things like this. Okay, so this is what we observe. That let's say I have a polynomial, let's say I just have a monomial. So consider this, f of x is equal to x to the n. We'll consider this. So that means by the definition, f prime of x would be equal to f of x plus h, which would be x plus h to the n, minus x to the n, that's f of x, all over h. Right? Those are n's, that's an h. Now, you've had to expand this before. If it was squared, you FOIL that out. If it was to the third power, fourth power, whatever. But in general, I want you to remember something from pre-calculus. I think you learned this in pre-calculus, which is called what is it called? The binomial rule. It's not called the binomial rule. It's a generalization about how to expand things like this. And the trick that you might have learned is that you can use Pascal's triangle. Remember Pascal's triangle? You've seen this before. Each number in the triangle is made by adding the two numbers above it. This is a 10 because that's a 6 and a 4 above it. 3 and 3 is 6. 1 and 2. You start with 1s up here, and then everything else fills in like that, right? 1 plus 1 is 2, 1 plus 2 is 3, and so on. And you go as far as you want there. Now these numbers here are the binomial coefficients. So for example, in this row, we call this the second row. You say, wait a minute, that's the third row. We call this the 0th row. So this is the 0, first, second, third, fourth, fifth row. So if you wanted to expand x plus h squared, instead of FOILing it out, you could just look at these and say, oh, that's x squared plus 2xh plus h squared. And you do have to, sorry, we're off screen a little bit there. You do have to know how the exponents behave, that the x's start maxed out and go down by 1 power, and the h's start h to the 0, and then they go up 1. You do have to know that, but you've done this enough that I think you understand how that works. So h plus h cubed, which is a lot more work to do the long way. The short way would be, it's 1x cubed plus 3x squared h. X's go down 1, h's go up 1, plus 3xh squared plus h cubed. And x plus h to the fourth is x to the fourth plus 4 x cubed h plus 6x squared h squared, and so on, right? So you can use these numbers. And what I want you to notice is that there's always the x to the n term. There's always the whatever you're raising it to the power. That number always shows up just like the second row, third row, fourth row, fifth row. So you definitely see a pattern in these first two terms. And that's really all we're going to need to know for recognizing this pattern. Okay, so that means here, when we expand this, we could say, well, x plus h to the n, I know that that's going to start off x to the n, right? And then I know the next term is going to be whatever power I'm raising it to. That's n x to the, and then if the power is 1 less each time, so it'd be the x to the n minus 1, and then times h to the 1 plus, and then this one gets a little bit messier to write an expression for. There's a way of doing it. You might notice that it's actually n choose 2 times x to the n minus 2 is h squared. I'd love to do a whole separate video or give you a lecture sometime about why it's this and what the connection is between combinations and Pascal's triangle and all that. But ultimately, it's not going to matter. The first two terms are the ones that are going to matter. We're just going to do dot, dot, dot here. Then minus x to the n all over h. So if you're busy copying that down, I would pause here for a minute maybe and try to make sure you understand where these first two terms came from. Okay? And how that matches up to the couple examples that we did here, writing them out. Okay, now notice that every time this is going to be x to the n, and we always have minus x to the n here. So that means we're going to have n x to the n minus 1 times h plus some number. It doesn't even really matter. I guess I could write that, but it's not going to matter what that number is. I'll see in a second why it doesn't matter. H squared dot, dot, dot. And every single term that comes after, that's part of this dot, 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 has even more h's in it than this, right? It's going to be h cubed, and then h to the fourth, and so on and so on, for as many terms as we have, all over h. And notice that all of these terms have at least one. This one has one h, this one has two, and so on and so on. So, and remember, our goal is to factor out an h so we can cancel out the 0 over 0 problem. So I'm going to go ahead and factor that h out. So factoring an h off this leaves n x to the n minus 1 plus, in this case it would be n choose 2, the x to the n minus 2, h. There's one h left here, right? That was squared, so one of them came out here. And then notice in our dot, dot, dot that there's going to be terms that still have h's in them, right? An h squared, h cubed, just one less h than they had there above. That's all over h. So you can cancel out the h's. And notice now, oh, you know what I did? Look at that. In all of these steps, I should have had the limit as h approaches 0. That's kind of sloppy there to leave that out. I'm just going to add that back in. So now that I've canceled out the h going to 0 problem, h going to 0, I can actually plug in the h. And notice that that means every single term here that still has an h in it, except for this one, it's the only one that doesn't have an h anymore, all of these are going to get knocked down to 0, right, because they still have h's. So that gives me that the derivative is n x to the n minus 1. And that is a powerful general rule to know. And that means if you have, remember this is the derivative of x to the n. So we could fill up a page real quickly with examples now. Let me just recopy. So our power rule is if f of x is equal to x to the n, then f prime of x, or in other words, the derivative of that, is equal to n, like the exponent kind of like comes out to the front, you can think about it that way, and then the new exponent on the derivative is 1 less than this. All right? That's the power rule. That's your first trick for taking derivatives and not having to do it using the definition. So let's crank out some examples. So let's see. That means I'll make a little table here. If this is f of x, we'll find the derivative. So f of x is x squared. So the 2 comes out to the front. It'd be 2x to the 2 minus 1, or to the first power. So the derivative of x squared is 2x. The derivative of x cubed is 3x squared. Power comes out to the front. The new power is 1 less. Derivative of x to the fourth is 4x cubed. Right? And going back to the last page, notice that. So the derivative of that is this. Right? It's like that second term that showed up in the binomial expansion. And so on and so on. You get the idea. 5x to the fourth. Now it turns out we don't actually have the tools to prove this yet, but I will tell you that this ends up working for any power, not just nice positive integers like this. It turns out that the derivative of, like for example, x to the negative 2 is the negative 2 comes out to the front, and then we drop that by 1. Remember, dropping that by 1 means it goes to negative 2 minus 1, that's negative 3. The derivative of 1 over x, well, 1 over x is the same as x to the negative 1, so that's negative x to the negative 2. Right? You've done this one before in homework. I think maybe you did this one too. And it also works for fraction powers, right? X to the 1/2, which means the square root of x is 1/2 x to the 1/2 minus 1 is negative 1/2. And we did this one before too, and your answer came out looking like 1 over 2 times the square root of x, right? But that's the same thing, right? So we need to be very comfortable getting from this notation to this notation, back and forth, which you learned in Algebra 2. Give you a little bit trickier example. If you had something like x to the 2/3, and the derivative of that is 2/3 x to the, think about this for a minute, what's 2/3 minus 1? You can pause and think about that for a second if you want to. That's negative 1/3, right? 2/3 minus 1 is negative 1/3. In my experience, the ones that trip people up the most are when you subtract 1 from the fraction and you get a negative number. Those are the ones that seem to vex people the most. And I think that's all the different kinds of examples that we're going to see. I will throw one other example out there. So what's the derivative of 2 to the 5th? Is it 5 times 2 to the 4th? You might think that it's that, but it's not. There's no x in here. 2 to the 5th is just 32, right? So if you had a function that looked like f of x equals 32, that's a constant function. It's a horizontal line at 32, right? Y equals 32. So what's the derivative or slope of that horizontal line? It's 0. Okay? Which brings us to the next part of what we want to talk about here. Other rules. These are all pretty common sense, but I think it makes sense for us to spell them out. So, first, we'll call this the constant rule, if you want to give it a name. If f of x is just equal to some number, we'll call it like c, a constant, then the derivative of a constant function, which would be a horizontal line, is always 0. Doesn't matter what the number is, the slope is 0. Here's an important rule. If f of x is equal to a constant times some other function, just call it g of x if you want, then the derivative is just equal to that constant times the derivative of the g function. It's possible, I'm not going to go through a proof of that. It's pretty easy to prove that using the definition of the derivative, but I don't think it's necessary for us to do that here. Let me give you an example of what that means. That means that if f of x is, let's say, 3x squared, then the derivative of that is, I'll look at the rule and give you a second to think about that. Well, it's a constant times x squared, and we know the derivative of x squared is 2x, right? So it's just 3 times the derivative of that, which is 2x, or in other words, 6x. So it's like if there's a number there, the exponent still comes out, it just multiplies into what's there. So if we had, like, what's the derivative of 4 on the square root of x? Well, that's the same as 4x to the 1/2, right? That's a better form for us, for our new rule. So that would be equal to 4 times the derivative of x to the 1/2 is 1/2 x to the negative 1/2, and 4 times 1/2 is 2. So it's 2x to the negative 1/2, and so on. That's a real easy rule to use. Another real easy one to use, which is very handy also, is if f of x is the sum, I got to give a different name here. If f of x is like g of x plus h of x, then what do you think the derivative is? It's the easiest possible thing it could be. It's just the derivative of that one plus the derivative of this one. And the same goes for subtraction. So instead of writing a new rule, I'm just going to add that in there. So that works for addition or subtraction. And that means that we can now do things like this. If f of x is, let's say, x squared plus 2x plus 1, then the derivative, we just go through and take the derivative of each piece. The derivative of x squared is 2x. The derivative of 2x is just 2. That makes sense, right? Because what's the slope of 2x? It's just 2, right? That piece taken on its own is just a line. So its slope is 2. Power rule still works here. The 1 comes out, multiplies by the 2, and then the power drops to 0, and x to the 0 power is 1. So it's like 2 times 1, which is 2. And then what's the derivative of 1? Well, by our constant rule, the derivative of any constant is 0. So you just go through piece by piece. I could give you more examples, but you get the idea pretty quickly here. 4x squared minus x plus 2. So the derivative of this, of x cubed plus 4x squared minus x plus 2, is 3x squared plus 8x minus 1, and the derivative of the 2 is 0. So that's pretty cool. A couple other little details here. First of all, we can now find higher order derivatives That sounds scary, but that's pretty easy to do. So what does this mean? If we write f double prime of x, that's what we call, that's the second derivative. Some people say the double derivative, but the second derivative of x. So what does that mean? It means find the derivative and then find the derivative again of your answer. It means, second derivative. Right? And give you an example. If f of x is something, then we could find the first derivative, and then we could find the second derivative. So if f of x was x cubed, the first derivative would be 3x squared, and the second derivative would be 6x. You might wonder, if you're a curious type of person, you might wonder, well, we know this means slope, right? That's the slope function. So what the heck does this mean? Does it mean something to take the second derivative? The answer is yes, but we're going to wait for a little while to attach a meaning to it. For right now, we're just going to define the operation of doing that. Of course, you could also, if you want, take the third derivative, right? What would the third derivative be? Well, it's just the derivative of the second derivative, which would be 6. And then after we do 3 of these little tick marks here, it gets a little crowded to do 4, 5, and so on. So if we have to do that, for whatever reason, the usual notation is to do this, to do f4, and we put the 4 in parentheses so we don't think that we're raising f to a power, right? So that's an indication that we want to do the fourth derivative. And the fourth derivative of this particular function, since we're doing the derivative of 6, would be 0. And then all the rest of the derivatives forever would also be 0, because we've got down to constant functions here. Right? Not all functions in the wide world of functions are always in y equals x form. So one of the great utilities of that dy dx notation is that we can find or have a way of writing derivatives for when we have functions that aren't just y and x. So consider, for example, here's some equations that you've seen before. I'll pull a couple from geometry. Here's c equals 2 pi r. Right? Here's another one. How about a equals pi r squared? And then one more. How about v equals 4/3 pi r cubed? You know what those are, right? It's the circumference of a circle, area of a circle, volume of a sphere. So if you consider r to be a variable, like a variable that could be the radius of any circle, and c to be like the dependent variable on that one, the circumference depending on how you change that, then just like we would write in something in y equals form, consider that to be like the y and this to be kind of like the x. Right? So we could say the derivative of this, we can't use y's and x's because there aren't any, but this is where the y would be. So I could say, instead of dy dx, I could say dc dr. Right? And we read this is the derivative of c with respect to r. We'll have more time to talk about why we say that with respect to. It's not the sense of like respect that you respect your elders. It's more like this is the variable that we're interested in. But anyway, more about that later. So again, this is the derivative of c with respect to r. That's how you read that. And what would the derivative of this be? Well, 2 pi is just a number times r to like the first power. So if that's our variable, like treating that like the x, would bump that out to the front, drop the variable, the power to 0, so the derivative would be 2 pi. Right? And pause and think about that for a minute if you want. So in this one, it's like y equals, there's our r is like the x, the variable again. So we would write the derivative of this dA dr, or in other words, the derivative of a with respect to r. And that's just a number. Pi is just a number, right? So that would be 2 pi r, right? By the combination of a couple of the rules that we've done before. And then here again, why don't you pause the video for a second and see if you can do this one. So we'd write dv dr is equal to 4 pi r squared. The 3 multiplies out to the front. changing 4/3 times 3 is just 4 pi r squared. Exponent drops 1. You might notice the very curious fact that whatever it means to take the derivative of the area of a circle, the derivative of the area comes out to be the circumference, and the derivative of the volume of a sphere comes out to be this, which you might recognize as the surface area of a sphere. So that's interesting, and we'll discuss later on at the end of this chapter why that is the case, why that's happening. That's certainly a very interesting fact, observation. And that is all you need to know for section 3.3. Of course, you can still find equations for tangent lines now. That's something else that you might be asked to do. This just gives you a faster way to do it compared to what we were doing in sections 3.1 and 3.2.